Okay, welcome back. In this video, I want to talk to you a little bit about how to calculate work, but for a spring problem, and just give you a quick example of that. These are actually relatively easy, especially compared to calculating the work from a pump of a liquid or something like that. So basically what we're talking about is you have a spring and there's going to be some sort of natural length where the spring sits at rest. So let's just say it is 5 centimeters, or actually let's put it in the proper units, 5 meters. Doesn't matter. That way I don't have to convert between centimeters and just keep things straight. Just remember that when you're calculating work, you want to try to get to joules or foot-pounds. So just remember those units, and joules is newtons times meters. So that's why I went from centimeters to meters, just to make things simple. Okay, so you have some sort of natural length, and let's just say you're going to be stretching that spring out. So the force associated with stretching that spring, if you remember Hooke's law, the force equals some sort of constant K, and then that distance that you pull that string out. So what's going to happen in your calculus class? They're probably not going to give you K. If they do, then there's probably some other trick in there. But instead of giving you K, they'll give you, I know the force to get to point 1, and then I'm going to ask you to figure out the work to go from this point to that point. And that'll be another force here. There's some distribution of force within that area there. But because we're talking about springs, it's going to probably just be this constant here. They may switch it up a little bit, but it's probably going to be this one. So they'll give you force 1 equals, say, like 10 newtons to get to move to a position of, and that's the trick, they'll probably say stretch it to 6 meters. So you have to know that I'm going to subtract 5 off of 6, and I'll have really 1 meter there. So force equals 10 newtons equals K, and then it'll be times 1 meter. So I'll be able to calculate K equals, just divide those, and that'll be just 10 newtons per meter. So then I'll have to apply that to the next location, or use this to figure out, basically, in calculating work, you have force along the x-axis or y-axis, and then distance along the x-axis. And you should always put this at the origin, should be your natural length. There. So I'll be subtracting 5 meters off of everything. But then your K is just going to be your slope coming up. Okay, so it's a change in y, which is force, over change in distance, or x. So in this case, that slope equals 10 newtons per meter. Okay, so looking at that, my function is just really 10x. Okay, so the equation for work is simple enough. It's the integral from b to a, and then it's just your function x, and this is really force, and then dx, the distance that you go through. Okay, so let's just say the second value is, we pulled it, let's say a total of 4 meters. And we want to know the work to go from 1 meter to 4 meters. Okay, so if my origin is right there. It's really just from 4 to 1. So the integral is 4 to 1 for the work. And then my f of x is just 10x dx. Okay, continuing along, if I take 10 divided by 2, x squared, and that's going to go from 4 to 1, is work. Then work is just going to be 5 times 4 squared minus 5, 1 squared, which is going to be equal to, is it 16 times 5, which is 80, and then minus 5, 75 Newton meters equals work. Or that's also 75 joules. So it's pretty easy. That's as simple as that. Just be careful about your units. Just be careful about making sure you take into account the neutral point. Just don't take the units that they give you. And then you're going to have to calculate for K using Hooke's law. And watch out for anything that they change up on you. So anyway, good luck. Hope this helps. You can subscribe to the channel, and I'll be continually posting different examples for different things throughout your syllabus. Thanks, and good luck.